So on this question, we want to find the derivative of y equals secant of 4x minus 2 plus e to the 7 minus x plus natural log of x squared minus 1. So one thing that I notice is that I have pluses between these terms here. And there is a derivative rule that allows us to focus on these terms individually. So because of this plus sign here, that means that I can focus on calculating the derivative of secant of 4x minus 2 separate from the derivative of e to the 7 minus x, separate from the derivative of y equals, not y equals ln of x squared plus minus 1. So when calculating the derivative, I'm allowed to calculate the derivative on these terms separately. Because they're individual terms. And then when I want to calculate the derivative of each one of these terms, I have to notice that these are the composition of two functions. So this first term has an outside function of secant and an inside function of 4x minus 2. And then we have the outside function being e and the inside function being 7 minus x. We have the outside function being natural log and the inside function being x squared minus 1. So all of these have the composition or one function substituted inside of another function. So we're going to have to use the chain rule to calculate the derivative on each one of these. So let's take a look at the chain rule. The chain rule So with the chain rule, let's write down what that rule is so that we understand it. And the chain rule deals with the composition. And the composition is when you have one function substituted inside the other function. So modeling what we have in our examples here, you have an outside function and you have an inside function. So when we have this composition, the way that we calculate the derivative is by following this pattern. And this is the shortcut for calculating expressions in this form. So what you do is you calculate the derivative on the outside function. Then we're going to leave the inside function the same, and then we're going to chain by multiplying by the derivative of the inside function. So we need to follow that pattern for calculating these derivatives that have a composition. So let's start with the secant of 4x minus 2. Our outside function is secant. So we need to follow the rule for secant. So what is the derivative rule for secant? The derivative of secant x is tangent x times secant x. So the derivative of secant is tangent times secant, or secant times tangent. So we have to follow that derivative rule for the outside. So the derivative rule for secant is that it will be tangent of something times secant of something. Now that something that's on the inside is the 4x minus 2. So that's the inside part staying the same, and then we have to chain by multiplying by the derivative of the inside. So our inside is 4x minus 2, The derivative of 4x is 4, and the derivative of negative 2 is 0. And so for that first term, we get 4 tangent of 4x minus 2 times secant of 4x minus 2. So we'll do the same thing with the next term. We're calculating the derivative of e to the 7 minus x. So because we have a composition, we're going to follow the chain rule, and we need to calculate the derivative on the outside function. So our outside function is e. Our derivative rule for e, the derivative of e to the x, is e to the x. So for the outside function, it's going to stay e. The inside function stays the same, but then we have to chain by multiplying by the derivative of the inside. The derivative of 7 is 0. The derivative of negative x is negative 1. And so really this becomes a minus e to the 7 minus x. So we'll do the next term. For the next term, our outside function is natural log. So we need to think of the rule for natural log. The derivative of natural log x is 1 over x. So for our derivative of natural log of x squared minus 1, we're going to do 1 over, and this x is the inside. For us, the x squared minus 1 is the inside. So x squared minus 1 goes in the denominator. Let's write that in blue so I'm being consistent. That's our inside, staying the same. And then we chain by multiplying by the derivative of the inside. The derivative of x squared is 2x. The derivative of negative 1 is 0. And so we get 2x over x squared minus 1. So we have the derivative being 4 tangent of 4x minus 2 times secant of 4x minus 2 minus e to the 7 minus x plus 2x over x squared minus 1. Okay, so I'm going to take the same example and explain it in a slightly different way. And this way of working out the derivative means that you are memorizing the derivatives in a slightly different way. So it really depends on your perspective of how you want to memorize your derivatives. So let me give you an example. So what you could do is you could memorize a derivative rule like this one here, the derivative of sine x. The derivative of sine is cosine. And then you could also memorize how the chain rule works. The derivative of f of g of x is f prime g of x times g prime of x. So if you memorize these two things, then you'll be able to calculate the derivative of any sine function, and then also if you put anything inside of sine that's different from x, you'll be able to handle it with this chain rule. So that's one way to memorize your derivatives. Another way to memorize the derivatives is if you memorize them with the chain rule already built in. So you could memorize that the derivative of sine u is cosine of u times u prime. And this is a way of writing the derivative with the chain rule built in. You see that we have our inside function. Our inside function stays the same, and we chain by multiplying by the derivative of the inside function. So I'm going to explain how we would calculate this derivative if you memorize the rules in a way that the chain rule is built in. So I'm going to erase all this. Let's write down the rules that you would have to memorize, and let's talk about calculating the derivative with those rules. So the three rules that we would have to have memorized would be the secant rule. So we're going to memorize this rule, the derivative with respect to x of secant u, and I'm memorizing it with the chain rule built into it already. So that rule would be that the derivative of secant u is secant u tan u times u prime. You would also need to have the derivative rule for e to the u memorized, and that would be e to the u times u prime. And you would also have to have the derivative rule for natural log. So the derivative rule for natural log of u is u prime over u. So now with these three rules, we're going to be able to calculate the derivative of each term. So the derivative of secant will be secant of u, whatever's inside, so secant of 4x minus 2 times tangent of whatever's inside, 4x minus 2, and then u prime, the derivative of the inside, is 4. Then we have e to the 7 minus x. That's going to be e to the 7 minus x times u prime. The derivative of what's in the exponent is -1. And then the last one, natural log of x squared minus 1. That's u prime over u. The derivative of x squared minus 1, that's 2x over x squared minus 1. And just to do a little algebra to simplify this, we would write this as 4 secant of 4x minus 2 tangent of 4x minus 2 minus e to the 7 minus x plus 2x over x squared minus 1. Okay, so on this question, we want to find the derivative of y equals sine squared of 5x. So what I'm going to do is I'm going to start by rewriting this in the typical form that we see exponents. We write with trig functions the shorthand so we don't have to write as many parentheses. But what this actually means is y equals sine of 5x, then all of that squared. So when I'm calculating the derivative of this particular function, I notice that I have a composition of functions, an outside function and an inside function. So my outside function is going to be the square, and my inside function is sine of 5x. So when calculating the derivative, I need to follow the chain rule because of this composition. So I'm going to calculate the derivative, and with the chain rule, we calculate the derivative on the outside function. So our outside function is a power. I'm going to follow the power rule to calculate that derivative. So with the power rule, I would bring that power down and take one away from that power. So that's calculating the derivative on the outside function. I'm going to leave the inside function alone, and then I'm going to chain by multiplying by the derivative of the inside function. So I've got to calculate the derivative of sine of 5x. Now, when I'm looking at sine of 5x, I also notice that this is a composition of functions. I have an outside function of sine and an inside function of 5x. So I'm going to have to use the chain rule again to calculate the derivative there. So let's carry down all of this. This is 2 sine of 5x. 2 minus 1 is 1, so I don't need to write that power there. And then using the chain rule, I want to calculate the derivative of the outside function. The derivative of sine is cosine. We're going to leave the inside function alone and chain by multiplying by the derivative of the inside. The derivative of 5x is 5. So putting that together with a little bit of algebra, we have 2 times 5, that's 10, sine of 5x times cosine of 5x. So on this example, we want to find the derivative for y equals log base 2 of x squared minus 1. Now this is one that I typically will forget the derivative rule for. So my first instinct is to go back to a little bit of algebra first. Some rules that I know about logarithms, and then I can rely on the derivative rule that I do have memorized in general, and that is that the derivative of natural log u is u prime over u. So this is the log rule for derivatives that I always keep memorized. This particular example has log base 2, and there's a different rule for the derivative of log with a general base. So what I do is I remember this algebra rule called the change of base formula. And this change of base formula allows me to change any starting base to a new base. And because this is the rule that I have memorized, I want to change it to natural log, which is base e. So the change of base formula looks like this. If you have log base b of, let's say, m, using the change of base formula, you can write it to any base that you want. So that's log base a of m over log base a of b. And if we want to use specifically natural log, it would look like this: natural log of m over natural log of b. So I'm going to rewrite this using that change of base formula. This is an algebra change, so notice I'm still labeling this as y, the original function. I'm not calculating the derivative yet. So this would be natural log of x squared minus 1 divided by natural log of 2. So what this does is it makes this 1 over natural log of 2 times natural log of x squared minus 1, and now I can use that derivative rule on this example. So to calculate the derivative, 1 over natural log of 2 is a constant multiple, so I just carry that down. And now I'll use the derivative rule on natural log of x squared minus 1. So that's u prime. The derivative of x squared minus 1 is 2x over u, which is x squared minus 1. And that gives me the derivative to be 2x over natural log of 2 multiplied by x squared minus 1. So that's if I don't have this specific derivative rule memorized. So that specific derivative rule is this right here, the derivative of natural, not natural log, we're doing any log. That would be log base b of u. That is u prime over u multiplied by natural log of b. So if I have that rule memorized right from the beginning, I could do y equals log base 2 of x squared minus 1. If I want to calculate the derivative of that, I need to do u prime, the derivative of the inside is 2x, over the inside, that's x squared minus 1, multiplied by the natural log of the base b, which in this example is 2. So you can see we got the same answer using both techniques for calculating the derivative. On this example, we want to find the limit, and this limit is, as x approaches infinity, of 2x minus 1 over 2x squared minus 3x minus 7. So if we were to use direct substitution on this one, we would end up getting infinity over infinity, which is one of our indeterminate forms. And so what I want to do is use a little bit of an algebra trick to rewrite this so that we don't get an indeterminate form. So with this algebra trick, what our goal is to make sure that we don't get something indeterminate overall, but more specifically, we try to produce a number for this particular position. This denominator, we don't want it to turn out to be 0 because that would be a problem. And we don't want it to work out to be infinity. So if we can get this to work out to be a specific number, and I'm highlighting this position here in particular because it's the highest power from the denominator. So that's why I chose this particular term. So if I can force this particular term to work out to a specific number, then I can force this to make sure it doesn't come out to be 0. And that's undefined. So my strategy is to take this x squared and we're going to divide it into both the numerator and denominator. And if we do that, just for example, if I divide this term by x squared, the x squareds are going to cancel and I'm going to get a coefficient in that spot. So I can make sure it doesn't work out to be 0. So my strategy is that I'm going to take the whole numerator, 2x minus 1, and divide it by x squared, and the whole denominator, 2x squared minus 3x minus 7, and divide it by x squared. I'll simplify. So to simplify, I'll divide that x squared into each term. That's using the distributive property. That's 2x over x squared minus 1 over x squared, 2x squared over x squared minus 3x over x squared minus 7 over x squared. We'll continue simplifying. 2x over x squared would be 2 over x. I need to make sure I don't forget my limit. That's the limit as x approaches infinity, and 2x over x squared is 2 over x. 1 over x squared doesn't really simplify. 2x squared over x squared is 2. 3x over x squared is a minus 3 over x. And 7 over x squared is going to stay the same. So now when we use direct substitution, we get 2 over infinity minus 1 over infinity squared over 2 minus 3 over infinity minus 7 over infinity squared. So another thing that we did, we turned each one of these fractions into something that we know how to calculate the limit of. When we have a fixed number in the numerator, a fixed number, and infinity in the denominator, infinity means that denominator is getting larger and larger. That means that this overall fraction is getting closer and closer to 0. Remember that your denominator is how many pieces you're dividing it up in, And so if you allow that to get larger and larger, the pieces become smaller and smaller. So each one of those pieces is approaching 0. So we get 0 minus 0 over 2 minus 0 minus 0, and that is 0 over 2, which is 0. So we get that limit as x approaches infinity of 2x minus 1 over 2x squared minus 3x minus 7 is equal to 0. So thinking of another approach on this example, when we are looking for limits at infinity, like we are in this example, this is when we're looking at the end behavior. What is happening at the very ends of the graph when x is infinity or negative infinity. And if we know about horizontal asymptotes, that's also helpful to know what the end behavior might be. So in an algebra class, you would study a function like this, and you would pay attention to the degree of the numerator. The degree of the numerator is 1, and the degree of the denominator, which is 2. And you'll notice that the degree of the numerator is smaller than the degree of the denominator. And so that means that we would have a horizontal asymptote at y equals 0. So at our ends, the graph will be approaching 0. The y value will be approaching 0. On this example, we want to find the derivative. And this says the derivative with respect to x of secant squared 5x. So when I'm calculating the derivative on this one, I'm noticing that I have secant, so I'll probably have to use the derivative of secant. But I'm also noticing this power and the 5x inside the secant, so I'm also going to have to use the chain rule on this one. So let's write down a few of the rules that we're going to use. So when I'm calculating the derivative, I'm going to have to use the chain rule, which is when I have one function inside of another function. And with the chain rule, the pattern that we follow is to calculate the derivative on the outside function, leave the inside function alone, and chain by multiplying by the derivative of the inside. We are also going to use the derivative of secant. The derivative of secant x is secant x tangent x. And we've got that squared, so we're probably going to have to use the power rule. The derivative of x to a power is the power times x to 1 minus that power. So let me first start by rewriting this so that we can figure out what is our outside and our inside function. And we need to know that for our chain rule. So the power on trig functions really means that whole function raised to the power, instead of the power only on that secant part. So this tells us that our outside function is the power, and our inside function is secant of 5x. So when we're calculating this derivative, we start by using the power rule to calculate the derivative on that outside function. So we bring the power down and take 1 away from the power. We leave the inside alone, and we chain by multiplying by the derivative of the inside. So we need to calculate the derivative of secant 5x. We haven't done it yet, so I'm putting the prime to say we're going to do it. So this gives 2 secant of 5x. 2 minus 1 is 1, so we now have that secant to the first power. And we want to calculate the derivative of secant 5x. So once again, I notice that I have an inside function and an outside function, so I'm going to have to use the chain rule again. This time secant is my outside and 5x is my inside. So I'm going to take the derivative of secant. Derivative of the outside function secant will be secant times tan. We want to make sure that we leave the inside of those the same, and we're going to chain by multiplying by the derivative of 5x, which is 5. So putting all this together, I'm going to multiply the 2 and the 5 together to make 10. I do have 2 secants here, and I can put those together and write this as secant squared of 5x. And then we still have the tangent of 5x. So our derivative is 10 secant squared of 5x times tangent of 5x. On this one, we want to find the limit. The limit as x approaches 8 of 1 over x minus 8. So our first option is always to try direct substitution. So when we try it here, we get 1 over 8 minus 8, which is 1 over 0. So this is obviously undefined. And even though it's undefined, it does give us some information about how we're going to approach the next steps of finding this limit. So what this information gives me is knowledge that at x equals 8, there's a vertical asymptote. So when you get this information, you have a non-zero over 0. And we have some theorems that tell us that anytime we get that non-zero over 0, then there is a vertical asymptote at that location. So we know at x equals 8, we have a vertical asymptote. Now, what does it mean exactly to have a vertical asymptote? When you have a vertical asymptote, this tells you that as x approaches that value, your y will approach infinity or negative infinity. So we know 3 possibilities for this limit now, because at vertical asymptotes, you can have a vertical asymptote where both sides are approaching infinity. And if both sides are approaching infinity, we would answer the limit as infinity. We could have a vertical asymptote where both sides are approaching negative infinity, and we would answer this limit as negative infinity. And then we have a third option where the sides are going the opposite way, where one is going to negative infinity and the others to positive infinity. And if we have that case, we answer the limit as does not exist. So if our asymptote is behaving in this way, we're going to be able to answer our limit as infinity. If it's behaving in this way, we answer our limit as negative infinity. And if it's behaving in this way, we answer does not exist. So once we've identified that we do have a vertical asymptote because of this, we need to figure out which case we're working with. So that's when we focus on the one-sided limits. So I want to see what's happening on the left and what's happening on the right so that I can figure out how to address this question. So to figure out what's happening on the left and the right, I'm just going to pick a number that's a little bit smaller than 8 and a number that's a little bit bigger than 8 so I can figure out positive infinity or negative infinity. So if I pick a number that's a little bit smaller than 8, like maybe 7.9, 7.9 minus 8 is going to give me a negative number in the denominator. So I know that on the left, I'm going to be approaching negative infinity. And on the right, if I pick a number that is a little bit more than 8, you know, some people just pick it up like this. They'll just write 8 plus because it doesn't really matter what the number is. But if I know it's a little bit more than 8 minus 8, that's going to be a plus. So I get a positive infinity. So that tells me that my asymptote is behaving like this, where one side goes to negative infinity and one goes to positive infinity. So that means this limit does not exist. On this example, we want to find the derivative of y equals sine squared x minus cosine squared x. So I'm going to start by rewriting these squareds in our typical format for squares. So this is the same thing as sine x squared minus cosine x squared. So now in this format, I can see that I'm going to need to use the chain rule to solve the problem. Each one of these terms has an outside function and an inside function. So the outside function is the power and the inside functions are the sine and the cosine. So I'm going to use the chain rule to calculate the derivative on each one of these. So with the chain rule, you always start by calculating the derivative on the outside function. So since our outside function is a power, I'll use the power rule. So we bring that power down and we take one away from the power. We want to leave the inside function alone and chain by multiplying by the derivative of the inside. So the derivative of sine is cosine. Now we'll do the same thing for the next term. The outside function is the power. So I'll use the power rule, bring that power down, take one away from the power. We want to leave the inside alone and chain by multiplying by the derivative of the inside. The derivative of cosine is negative sine. So with a little simplification, we end up having 2 sine x times cosine x minus 2, actually this will be plus, if I multiply together this negative and this negative, it becomes a plus. So plus 2 cosine x sine x. And these are like terms, and I can combine those together. So it becomes 4 sine x cosine x. Now this answer is perfectly acceptable. You can stop here, but some people would notice when you see a sine x times a cosine x, it reminds you of some of your trig identities. There's a trig identity called the double angle identity that looks something like this. 2 sine x cosine x is equal to sine of 2x. So using a double angle identity, you can write this as 2 times 2 sine x cosine x, and this part right here, using that double angle identity, would become sine of 2x. So we found the derivative of sine squared x minus cosine squared x to be 2 times 2 sine 2x. Excuse me, I think I misspoke there. The derivative is 2 sine of 2x. On this example, we want to find the derivative of f of x equals e to the x plus 1 over square root of x. And we have a fraction bar here. So we're going to use the quotient rule to calculate the derivative on this example. Not only that, it will be helpful if we rewrite our denominator so that we can use the power rule. So I'll write this as x to the 1/2 power. And let's also write out what the quotient rule is. So the quotient rule is the derivative of f over g is the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator over the denominator squared. So that's the pattern that we're going to follow when calculating this derivative. So f prime will be our denominator, x to the 1/2 power, times the derivative of the numerator. The derivative of e to the x is e to the x, and the derivative of 1 is 0. So that gives us the denominator times the derivative of the numerator minus the numerator, e to the x plus 1, times the derivative of the denominator. So this is where it gets a little bit messy, because the derivative of x to the 1/2 using the power rule would be 1/2 x to the negative 1/2. And we want to divide by the denominator squared, so that's x to the 1/2 squared. So we've calculated the derivative, but we're going to do a little bit of cleaning up to make this expression look nicer. And what I'll do is I notice that I have a fraction here, and that makes the problem a little bit messy. So I'm going to write a 2 over 2 in the other term so that I can factor out that fraction. 2 over 2 is the same thing as 1, so I'm able to multiply by 1 anytime. I also notice that I have x, a factor of x on the first term and a factor of x on the second term, and I'm going to factor out the lower of the two powers. So we have 1/2 x to the negative 1/2 as to what we're factoring out. So I factored out that 1/2, so that's gone. So I'll still have a 2. And when I factor something out, I'm dividing it out. So I can think of it as x to the 1/2 over x to the negative 1/2. And then I also have that e to the x. So I wrote it in this way right here because it can be difficult to figure out how you can factor out this negative exponent. So I think of the factoring out as dividing out to help me understand it. In the next term, I will still have an e to the x plus 1. That 1/2 gets factored out, and the x to the negative 1/2 gets factored out. In the denominator, x to the 1/2 squared simplifies to be x. And I'll continue simplifying inside here. So using my exponent rules, because these have the same base, I can subtract these exponents. So that's going to leave me with 1/2 x to the negative 1/2 times 2x to the first power. 1/2 minus negative 1/2 is 1 minus e to the x minus 1. The final thing that I'll do here is I'll send this 2 to the denominator, and I'll send this whole term to the denominator because it's got a negative exponent. So that'll give me 2x e to the x minus e to the x minus 1 over 2x to the 1/2 times x. And I can even go one step further and combine these two together since they have the same base. That becomes 2x e to the x minus e to the x minus 1. When I multiply with the same base, I add the exponents. So 1/2 plus 1 will be 3/2. That's x to the 3/2. And we can even do one more thing. We can turn that back into a radical to make this 2 square root of x cubed. So the derivative was calculated with the quotient rule, and then most of the work afterwards was you doing some algebra cleanup to make that derivative look nice. So on this one, we want to find the derivative of f of x equals x times 2x minus 5 cubed. And on this example, I notice that I have a product, x times the 2x minus 5 cubed. So I'm going to use the product rule. And then on this particular factor, I have 2x minus 5 to the third power. This is a composition of two functions. So I'm going to have to use the chain rule when I'm calculating the derivative on that particular factor. So I'm going to use the product rule, the chain rule, the power rule on this example. So we're going to calculate the derivative. I'm going to follow the product rule. And with the product rule, I would do the first factor multiplied by the derivative of the second factor. Now this second factor was kind of complicated, so instead of calculating the derivative right now, I'm going to save it until I've written out the rest of this product rule. So I've got the first factor times the derivative of the second factor plus the second factor times the derivative of the first factor. The derivative of x is 1. So now we need to focus in on calculating the derivative of 2x minus 5 cubed. And as I said earlier, this is one we're going to use the chain rule. So we've got to identify the outside function and the inside function. So we've got the cube being the outside function and 2x minus 5 being the inside function. I usually write the inside function in blue, so let me switch that. So the chain rule says that we calculate the derivative on the outside function. So that's the power rule, bring the power down and take 1 away from the power. And we leave the inside alone. We leave the inside alone, the 2x minus 5, and we chain by multiplying by the derivative of the inside. The derivative of 2x minus 5 is 2. And I'm going to copy down this 2x minus 5 cubed. And we can write this as I can multiply the x, the 3, and the 2, so this becomes 6. 6x times 2x minus 5 squared plus 2x minus 5 cubed. So we have calculated the derivative here already, but I'm going to use a little bit of algebra to clean this up. So what I notice is that I have a common factor of 2x minus 5, and I can factor that common factor out. And I'm going to take the lower power, so the squared is the lower power. If I factor that out, I'll be left with 6x. And since I'm factoring out two factors of 2x minus 5, and this has 3, I'm still going to have one more factor of 2x minus 5 left. Let's simplify inside those brackets. 6x plus 2x is 8x. And so we get 8x minus 5. So our derivative of x times 2x minus 5 cubed is 2x minus 5 squared times 8x minus 5. Thank you for checking out my videos. Have a great day.